Imagine spending years building a new rocket that's supposed to secure Europe's future in space. Launch day finally arrives. The engine starts normally. The rocket clears the tower. And for the first 30 seconds or so, everything looks perfect. Then, both navigation systems crash. The rocket suddenly turns, breaks apart, and destroys itself, just 37 seconds after the main engine was ignited. And here's the really strange part. The engines were fine. The weather was fine. Even the physical navigation equipment was still healthy. The rocket was lost because software borrowed from an older rocket tried to process a number that was too large. But behind the number was a bigger chain of old assumptions, identical backup systems, and a test nobody performed. So let's take a look at how Ariane 5 Flight 501 managed to fail in less than a minute. Before Ariane 5, Europe had the successful and reliable Ariane 4, but satellites were getting heavier, and Europe wanted a more powerful rocket that could carry larger payloads and handle future missions. That's where Ariane 5 came in. It wasn't just an upgrade, it had more powerful engines, a different design, and, this will matter later, a very different flight path. Its first flight carried 4 scientific satellites for ESA's cluster mission. They were supposed to fly together and study how the solar winds interact with the Earth's magnetic environment. So this wasn't just a new rocket. Scientists had also spent years preparing the 4 spacecraft sitting on top of it. On the morning of June 4th, 1996, the countdown at Kourou in French Guiana went smoothly. Poor visibility caused a short delay, but the weather improved. At 9:33 local time, the Vulcain main engine started. About 7 seconds later, the solid boosters fired and Ariane 5 lifted off. For roughly 30 seconds after leaving the ground, the flight was normal. Then, at about 36.7 seconds after the main engine started, the backup navigation system shut down. Around 50 milliseconds later, the active system shut down too. And at that point, the rocket no longer knew which way it was pointing. Instead of relying on one navigation computer, Ariane 5 carried 2 inertial reference systems. They used laser gyroscopes and accelerometers to measure how the rocket was moving and which way it was facing. One system was active, the other was ready to take over, for a random hardware failure that probably would have worked. But there was a problem. The 2 systems had identical hardware, and more importantly, they were running identical software. So yes, Ariane 5 had a backup, but the backup had exactly the same hidden weaknesses as the main system. It was like copying a key that doesn't fit the lock. You now have 2 keys, but you still can't open the door. The navigation system inside Ariane 5 was based closely on one that had already worked on Ariane 4. Part of its software aligned the navigation platform before launch. Basically, it helped the system work out its exact orientation while the rocket was sitting still. On Ariane 4, this alignment function stayed active briefly after the final launch sequence began, and there was a good reason. If the countdown stopped during its final seconds, the launch team could restart without waiting 45 minutes or more for another alignment. That could save a mission with a short launch window, and the feature had actually been useful in 1989. But Ariane 5 used a different countdown sequence and didn't need the feature. Still, the old function remained because it had already worked reliably on Ariane 4. The thinking seems to have been, if we don't need to change it, why take the risk? That doesn't sound unreasonable. Changing proven software can introduce new problems, but leaving it unchanged is also risky when you move it into a machine with a very different behavior. The old alignment function continued for around 40 seconds after liftoff, doing calculations that were no longer useful. And that useless calculation was about to bring down the entire vehicle. Inside the alignment software was a value called horizontal bias. The name isn't important. What matters is that it was connected to the rocket's horizontal movement. Ariane 5 accelerated differently from Ariane 4. Its horizontal velocity increased about 5 times faster, so the software saw a much larger value than it had ever encountered before. Then, the program tried to convert the value from a 64-bit floating point number into a 16-bit signed integer. In simple terms, it tried to put a large number into a smaller box, and it didn't fit. A 16-bit signed integer can only go up to 32,767. The value inside Ariane 5 was larger than that, so the conversion produced an error. The engineers knew conversions like this could be dangerous. They had identified 7 variables that might cause the same problem. 4 were protected, 3 were not. Horizontal bias was one of the unprotected ones. Why? Partly because the navigation computer had a workload limit, and partly because those 3 values were believed to be physically limited. They weren't supposed to become large enough to cause an error. That belief made sense when you looked at Ariane 4. Nobody properly checked it against the flight path of Ariane 5. The result was an unhandled conversion error, and the backup navigation processor shut itself down. Then the active system reached the same calculation, saw the same oversized value, and shut itself down for exactly the same reason. You might think the rocket simply stopped receiving information. What happened was worse. The active system sent diagnostic information onto the rocket's data bus. The onboard flight computer interpreted this diagnostic pattern as if it were real flight data. As far as the computer could tell, the rocket had suddenly moved in a way that hadn't actually happened, so it tried to correct the imaginary problem. It commanded the nozzles of both solid boosters and then the main engine to turn almost as far as they could. Ariane 5 changed direction violently. The rocket reached an angle of attack of more than 20 degrees. At that speed, the aerodynamics forces were far too strong for the structure. At about 39 seconds after main engine ignition, the rocket started breaking apart. When the solid boosters separated from the central stage, the onboard safety system detected the breakup and destroyed the vehicle, exactly as it was designed to do. The explosion happened at an altitude of around 4 kilometers, only about 1 kilometer from the launch pad. The rocket and all 4 cluster satellites were gone. Now this is the part of the story I found most interesting, because the failure could have been discovered. The equipment and flight control system had been tested, but nobody combined the real navigation software with realistic Ariane 5 flight data in one complete test. At equipment level, the inertial reference system was tested thoroughly, but the tests didn't include the actual trajectory of Ariane 5. Then, during the larger closed-loop flight simulations, the real inertial systems weren't used. They were replaced by software models that generated the navigation outputs the rest of the rocket expected to receive. Those models were useful for testing the flight computer, but they didn't run the real alignment code, so they couldn't reveal the dangerous conversion hidden inside it. The navigation system was considered qualified because it had worked on Ariane 4, and using real equipment, in a full simulation would have been difficult, but together those decisions left one enormous gap. Nobody tested the real software on the real navigation computer using the movement of the new rocket. After the accident, investigators did exactly that, and the simulation reproduced the failure. So, was Ariane 5 destroyed by a number overflow? Technically, that started the chain, but everything around it allowed the problem to grow. An old function that wasn't needed during flight was still running. An assumption from Ariane 4 was carried into Ariane 5 without being checked. A dangerous conversion wasn't protected. One software exception was allowed to shut down an entire navigation system. The backup contained the same error. Diagnostic information was mistaken for flight data, and the complete system was never tested under the conditions it would actually experience. The code did what it had been designed to do. The real failure was in the assumptions connecting that code to the rest of the rocket. The investigation recommended switching off the alignment function after liftoff. It also called for more realistic tests with real equipment, clearer documentation of system limits, better exception handling, and a full review of critical flight software. The program didn't end there. Europe fixed the problems and completed a fully successful third qualification flight in October 1998. Its first operational mission followed in 1999. Ariane 5 eventually became one of Europe's most important launch vehicles. But its first flight left behind a lesson that applies to almost any complicated system. A backup isn't really independent if it can fail for exactly the same reason as the original. Old software isn't automatically safe just because it worked before. And whenever you move something proven into a new environment, all of its old assumptions need to be questioned again. Flight 501 was destroyed in seconds. But the decisions that made the failure possible had been building up for years. If you like stories like this, where the real failure is hiding behind the obvious one, you'll probably enjoy the rest of Failure Atlas. So feel free to subscribe. And if you found this one interesting, a like really helps the channel get started. This is Failure Atlas.